Right, hopefully you've had another look at this little video on YouTube. This is a train approaching the station, which perfectly demonstrates the Doppler effect. Right, what you'll notice is a change in pitch. So as the train's approaching, the pitch of the train whistle is high pitched, and after it's passed, when the train's moving away from the observer, the train whistle sounds low pitched. Okay, so that is called the Doppler effect. But in this short video, I'm going to explain exactly why this happens. Okay, well, so it's all about frequency and pitch. Now, got quite a cool little demonstration here on YouTube. I'm going to quickly run through you. Now, this is the best thing I can find for explaining how the Doppler effect works. Right, let's just set the scene. We've got a bee. Okay, we've got a buzzing bee, and we've got a microphone. So the microphone's the observer, and the bee is the wave source. Okay, so that's the observer, the microphone, and the bee's the thing making the sound. Now these circles here, these are the sound waves. These are the individual sound waves which are going to be moving outwards in all directions from the bee. Now, what happens if the bee moves relative to the observer? That's the important thing. Right, let's quickly run through it. Okay, right, now the bee is approaching. Can you see? Now, what happens to the sound waves in front of the bee? Because the bee's moving towards the observer, the sound waves get bunched up. Can you see that? Now, because the sound waves are getting bunched up, the wavelength is getting shorter. Now, if you remember from yesterday's lesson, if the wavelength of a sound wave gets shorter, the frequency goes up. So the pitch is high. So when the bee's approaching the microphone, the buzzing from the bee is going to sound high pitched. All because the waves are getting bunched up. So the frequency is actually increasing. Okay. What about if the bee's moving away? Okay, there we go. Bee's moving away for the observer. What happens now? Well, it's the opposite, isn't it? It's because the bee's moving away and the sound waves are going in the opposite direction, the waves get stretched out. Can you see the wavelength has now increased? Now, it's exactly the same thing, but the converse. If the wavelength gets longer, the frequency goes down. So the waves here hitting the microphone will sound lower pitched because the frequency has gone down. It's all to do with relative motion between the wave source and the observer. If the bee's stationary, like we had at the beginning, like that, if we had the bee stationary, then it doesn't matter whether the microphone's here or here or here or here, because the wavelength is the same, the bee will just sound normal. It's only when the bee is either moving towards or away from the observer. So there you have it. That's what causes the Doppler effect. Right, just a couple more videos for you to look at now after this one. Okay, we've got me demonstrating the Doppler effect in my living room. And then I want you to do a short Google Doc I would like you to complete after this